what we have here are three 1 kilogram weights suspended from a spring. We see that the weights will bounce up and down on the spring. Now right now I have more than just the 3 kilogram weights. I have some, let me grab one of these. I have some 100-gram masses. I've got 3 of them sitting here, 1 in between here and 3 in between here. That's a total of 7. I'm going to be able to add 2 more of these to make 9. So now I have 9 masses, each 100 grams, so I have 900 grams of mass on this system. And I can measure the height of this end. Seems to be about 36.9 centimeters, give or take a millimeter. Now if I take these off, of course, the system is going to rise up. And now we have about 39.9 centimeters. So we see that we had a rise of about 3 centimeters due to the 900 grams that were added to this system. The 900 grams, of course, caused the system to stretch out because gravity was exerting a force in that 900 grams. The spring had to support that extra force, and in order to support that extra force it had to stretch out so that the restoring force would be sufficient to overcome the extra gravitational force. From that information I can calculate the restoring force constant K, which I can then put together with the mass of the system. Now there's a little bit of mass in this spring, so the mass of the system is effectively just a little greater than 3 kilograms. But if I put all that information together, I'll get a pretty good approximation, and then I can measure the period of this motion using my timer. I can count 10 or 20 oscillations of this motion and determine the period of motion, which allows me to determine the angular frequency, omega, for this system. And I can check that with what the theoretical prediction is based on the mass of the system and the restoring force. The restoring force constant, that is.